Welcome, Chris. Thank you.
Thanks, guys. It's always a little awkward to hear something your wife wrote come out of the mouth of another woman. Sorry, I hope that wasn't bad. On to the topic at hand. Netflix. So how many of you guys are Netflix subscribers? All right, look at that. Check that out. How many of you are DVD subscribers? That's faithful, strong. I like it. I like it. How many of the people that raise their hand as subscribers have had a rebuffering issue in the last 30 days, we'll say? Okay, so well, that's kind of crappy, actually. I ask these questions at the start of each talk I give, just as like a reference point to kind of gauge what's happening in the audience's awareness with the product. The reality is that there's a ton of people that are using Netflix, and as context, what we're going to do is I'm just going to start with a little bit of background about Netflix. We'll talk about the architecture. We'll talk about, that'll get into anomaly detection and why we're changing the way that we're thinking about things slightly. And then we'll leave some time for questions at the end. So yeah, a ton of people are using Netflix. I think this is pretty well-known fact at this point that Netflix peak hours represents about a third of all downstream internet traffic. 36.5% technically, but there's about 100 million hours of TV and movies watched a day, which is that's a mind-blowing number when you think about how it's pretty sweet. And then the last thing, which is just super exciting for us, is that we're currently at 70 million customers with our current global footprint, which is 50 countries, and by the end of next year, we're committed. Well, we're not. I guess we haven't formally committed to it, but we have a goal of being fully global by the end of next year. And so, we're going from 50 countries to 250 countries. These numbers are only going to get bigger, and the ability to process data efficiently and think about where we're falling short is only going to become more and more critical, which is why we're investing pretty heavily in this. And when the service goes down, people let us know, right? So this is something that happened literally on Tuesday of this week. I wish I could say I was responsible for the code push that was responsible for this, but unfortunately, fortunately, maybe I wasn't. And so because people are mad when we do bad things to them, it makes sense for us to just really be thoughtful with the service that we're providing for them. So just to put this, one last data point to put this in context is, this is the current public number. We have 500 billion events per day logged, and that's only to our control plane. That's not even data logged to the CDN. So if you think about a third of all downstream internet traffic, that's the internet traffic that you're receiving in bytes and bits to put on the screen. This is the data that we're receiving back from you. And this number really blows me away. It kind of shocks me as a consumer myself, because to think that I'm just one part of one company that's building this much data on me as a consumer, there's a question there about the utility of that data. And so I think we have to be really smart about what we keep and how we use it. And the other thing that's interesting is that, at Netflix we do roughly 40 code pushes a day. So when you have hundreds of microservices, and any one of those could be causing some upstream or downstream fallback or any number of problems, it's really hard to isolate exactly what the issue is. And so this is just more motivation for why we're investing so heavily in what we're doing. Okay, so this is what outage looks like when you're looking at 50 billion events, on Tuesday, November 10th, right? So I want everybody to kind of look at that and just for a second think about at what point did the data become such a discrepancy from what is considered kind of normal or acceptable that you should have raised a flag and said, yeah, something strange happened here. I mean, don't answer internally. I'll give you a couple hints. So the first hint is that the black line that's not like our predicted or expected value. The black line is the data from last week, right? So it's just like historical data. It's not really representative of anything. And the red line is what the data was from today. Right, so I hope everyone's got a little point in their mind. That's where it actually was. So when I look at that, I say, shit, there's no way that we're going to be able to figure out that that there's an outage happening right at that point in time. I mean, if I were to look at this and know nothing, I would have said the outage happened in the first 3 hours of the day. Didn't happen, right going into our peak traffic. All right, so before I talk about how we're actually solving this problem, I'm going to spend some time talking about the architecture. And this is to serve two purposes. One is just to give you a sense of how we operate and how we're scaling and the direction that we're going as a company, which I think is super interesting and relevant, and people are passionate and care about that. And then the second is, this is just more super relevant information for why we're making the decisions that we're making. Okay, so I don't think it's a secret that we're a huge Amazon shop. I think Amazon is happy that we're a huge Amazon customer. I will say there's been maybe one of the most proud moments in my career was been a time when we requested enough nodes that Amazon came back and said we don't have that many nodes in our I'm not even going to say what data center was. Yeah, we're a huge Amazon customer. It's also not a secret that we're a huge Hadoop user. And I know that right now, the vast majorities of companies are interested in moving towards Spark, and we are too. I'm not saying that we're not doing that, but the reality is that Hadoop is still an old faithful that's been able to process data if we have 500 billion events a day, and we're trying to analyze the last year of data, which is what we do for all our recommendation algorithms. Like, the reality is that there's no way that some of those other platforms are going to be able to scale to that data volume. And so we have to be here for right now, and as the other technologies evolve, we're going to adopt them, but for right now, this is still where we are. Our distribution of Hadoop is a little different because we use EMR, so we're not using HDFS in the same way that most companies are using HDFS. Instead, we use S3 as kind of our persistent data store for all of our data. So anytime we want to persistently store something, an aggregate or a fact, for an indefinite amount of time, we use S3 to do that. And this gives us flexibility to roll out into other tools, to roll that data directly into other tools. This does come at a cost, though, because it's much more expensive from a time and compute perspective to write to S3. It's like a 10x slower latency to write to S3 than it is to write to native HDFS. So for this point, we've gone through painstaking iterations with AWS to make sure that we're writing to all intermediate objects to HDFS instead of S3 and things like that. But this is kind of our core strategy. And that enables us to do some really interesting things. So 500 billion events a day comes through currently what we call the Suro pipeline, that's like our variant of Chakwa, which is Chakwa is a predecessor to Kafka. We're currently in the process of migrating to Kafka itself, so we actually have a shadow pipeline. So we're processing 500 billion events twice a day, which is kind of a crazy thing to think about. And then all of that is written to S3, and then that doesn't include any of the data that we extract from the raw online services. So like Cassandra, for example, is a data store that we use for heavily for all of our online services. And so to extract data out of that, we have a native tool that we've built ourselves called aggregate. Try to say that twice fast. And it's elegant in the way that it's been integrated with Pig so that we can just naturally cascade data through all of our data pipelines and persist them in S3. Like I said earlier, Pig is kind of like our core tool for processing. Pig on Hadoop is our core tool for processing things. And when business logic gets particularly complex, we use Python. There are a couple people out there that still use Hive, but for the most part, we're still a pig shop. There's no real data processing that happens in Teradata or any relational data store, but we do use these for the purpose of maintaining data that we want visible for visualization purposes. And these are like MicroStrategy and Tableau, kind of basic pivot chart and line charts and things like that. Of course, they can do more sophisticated things, which we've taken advantage of in kind of case-by-case basis. But for the most part, this is just enabling people to get at the data themselves in a self-service way. We also have built a super lightweight pivot chart kind of capability called Sting, which is you just point it at an S3 bucket, and it goes and it extracts all the metadata that you could possibly want on that set of files, and it figures out how to index it so that you have really responsive, I guess, discovery of your data. And then for interactive queries, we use Presto heavily. So Presto is much better than Hive and Pig, if you're not aware, because it reuses Java containers. So you don't have the latency of to spin up JVMs, spin up and spin down JVMs. So this is like super efficient for just rough queries or really basic aggregates to make sure that your data is in acceptable condition. And then Druid is kind of new to the camp. We use Druid as a back-end data store for all of our A/B testing. So we have maybe one of the most sophisticated tools that we've built in-house is our A/B testing framework. And as a back-end for the node layer there, we have Druid to perform all the aggregates. And this data starts to get really big when you start to think about like share of discovery hours or share of play hours at a user level. So you have to aggregate to the user level and then normalize across users and then aggregate across titles. And when you have to do multiple ags like that and share data, it can get expensive, but Druid's particularly good at this. But the big downside of Druid is it's super inflexible. So once you impose a schema on it, you're not going to be able to change it at all. And then the newest member is Spark, and adoption is growing rapidly, but it's still not super high. And I think mostly because that's because of the pain that you experience when you start to pull in like a petabyte a day. All right, so I just threw the data platform at you. I'm going to take one more second to talk about how data gets to S3, just to clarify that a little bit more, and then we're going to talk about how we take advantage of all this data. All right, so this is the current data pipeline. So we have all these microservices, which are basically applications that are logging data to S3. They currently hit Chakwa and then are either redirected to a Kafka cluster for like local processing and routing to these various downstream services, or that goes directly to S3 where it's persisted and processed by Hadoop. There's also a small process between Suro and S3. It's not really between it technically, it's kind of like a layer on top of that, which is called Ursula, where Suro will write many small files, and when you try to process many small files, you can have problems with listings. And so what Ursula does is it comes and it aggregates small files within the same partition up to modestly sized data sets. But what we're moving towards is much more simpler. It doesn't, I think it's simpler. It's basically getting rid of Suro and just replacing it with Kafka. But it's much more elegant, and it allows us the ability to streamline all of our APIs and also think about the way that we can start doing stream processing. I should mention one other thing. So I said that this is the source of the 500 billion events. That's true. We have an additional data source, which is the extracts from Cassandra. And then we have a whole separate pipeline, which is our real-time operational metrics. So these are like basically keep alive metrics that is called Atlas, and that's a completely different pipe. And we're not going to talk about that, but it's there too. Okay, so this is like all the customer data that we basically persist. Atlas is all the service data that we don't really want to, persist for the long term. Okay, so when data is written to S3, Hadoop naturally has the idea of metadata contained in the headers of each file. And you can think of, as Hadoop has been maturing, and the way that HDFS, as the way that file formats have been maturing, the amount of information and the complexity of that information has been increasing. And you could take that to a logical limit where you might actually have a service that manages all the metadata associated with all the files that you're trying to process. And that's what Metacat is. It stands for Metadata Catalog. And this is a service that we've built to do exactly what I just said, maintain all this metadata. And this is an incredibly rich source of information for when you start to think about data quality. How great would it be, imagine this for a second, if rather than having to read your entire data to try and figure out whether or not something was wrong, you could just look at the metadata and analyze the metadata and figure out that there was something wrong with the distribution of, say, some column in your table, or the set of keys that was in your table changed. So that's what Metacat is. It's literally a service that, as data is written, there's a file that's written, there's a commit to the Hive metastore, and then there's a commit to the Metacat, and then the operation returns, and your write is complete, if you will. So, and all this data is accessible via the Big Data API, and it doesn't store just metadata about what's in the files. It also maintains a list of all data about who consumed that data, where it went, all the downstream consumers, all the upstream producers. It's a super rich data set, and it's got an API, so you can just go hit it and get everything that you want for free in a pandas data frame, which is pretty sweet. So that's like the context for what we're talking about. And now we're going to talk about anomaly detection. So we started by proposing a new type of Metacat metric. And you can imagine that any data set think of it as a huge matrix, right? Even though it's maybe a set of rows with different keys and different values, think of it as just a huge matrix. And every table has a different dimension, just not because it's required, but just because it's like the blue sky theorem, right? The sky's big, and you're eventually going to hit something. You wait. It's big enough so that you probably won't hit anything. I think I got that wrong. Anyway, but the idea is that you have a bunch of arbitrarily sized matrices that are coming in, and these have roughly, let's say, 10 billion rows per partition and maybe 100 columns per row, right? And we want to take this data, and for every data set, no matter how big it is, we want to map it into some smaller data set that's roughly, order 10 by 10, right? So we're going to take all the data that's encoded in this extremely large matrix and try to represent the probability distributions of all of those columns and all of those rows as a matrix that's 10 by 10. And we can do this through some really elegant hashing. We're actually working on a paper right now where we're going to talk about how we use different types of hashing methods to get at different probability distributions and accurately capture and represent them. But the ultimate point is this, that now for every data set that's written to Hive, we have, instead of having to keep some massive some massive aggregate, right? We keep some very small, reasonably sized aggregate that we can process later. And here, I'm not gonna show you a time history of 100 values, right? But I'm gonna just select 4 that all correspond to one key, so that you can get a sense of what these things look like. And it's a little messy, so beware, but it's not like surprising. So here, this not surprisingly has the same kind of shape that you saw in the previous slide, right? When I showed you where the outage was, we had this kind of gradual ramp up and then kind of sustained peak and then a sudden drop off, right? So this is that same trend over multiple days. You could probably guess where, if you spend a lot of time, you could probably guess where weekend days are and where weekdays are and things like that. But the other thing is that by looking at these hashed values, right, the mapped values of these hashes, natural trends emerge that are extremely stable and very, very periodic, right? And so, you have this like dark black line that's, kind of, it's higher than all the others. And you have this kind of semi-grayish line that's got 2 spikes in it, but the spikes are incredibly periodic, right? The periodicity of these spikes it's incredibly consistent. So the reason that we're looking at this is because you can start to see where we've completely naively, this is on the second to last day here, we're going into Wednesday, but this is the Tuesday that we had that outage, and you can see we have much more sensitive metrics that capture this outage, and I wish I could, well, I think you guys can see it, right? It's kind of on this hub. And this is just 4 metrics, right? So we actually have this across about 60 of the metrics. And what we do ultimately is we do anomaly detection via multiple algorithms and on these different hashes. And then we, via consensus, we try to decide whether or not there's an anomaly or not. All right, so what's our core anomaly detection algorithm? The core anomaly detection algorithm right now, we're A/B testing an alternative, is RSVD, or RPCA. It was originally proposed in a paper by Candace. And this is, it's a beautiful paper if you want to go read it. He basically proposes a way to decompose a matrix into 3 parts. One, a low rank part, a second, which is a noisy part, and a third, which is a sparse component. So this is differentiated slightly from, PCA, which is, in PCA, you're just trying to decompose the different parts of the variance, right? But here, you're actually trying to decompose it into these kind of 3 distinct, sets. And so those are represented in the solution as L, E, and O, where L is the low rank, E is the error, right, error distribution, and O is the anomaly or outlier or sparse component. So here's how we use this algorithm. You can imagine you have a one-dimensional time series of data, right, that's going on for some, period. And so imagine that time series is periodic. And then imagine that you have one signal for each day, and you're going to re-express that, you're going to reshape it into a matrix with n number of rows and 7 columns, where each column corresponds to a different day of the week, and each row corresponds to a different day over the last n weeks. I'm sorry, each row corresponds to a different week over the last n weeks. So it's a supernatural idea, and it's currently, I think about it most frequently in the kind of daily use case, but I've presented it to you already in the hourly use case. And once you have this matrix X, you can really do any matrix decomposition on it, right? And so now we're just going to walk through the steps of RPCA so that you get a sense of how it works. And then I'm going to talk about some other applications of how we're doing using RPCA for anomaly detection in other spaces. All right, so we're going to start by doing vanilla singular value decomposition. So how many of you are familiar with singular value decomposition? All right, so I don't need to explain this too much. Basic idea is that U represents the row space, right? So all the information that's happening across the weeks is kind of encapsulated in the row space. V transpose represents anything that's happening across columns, right? The first, so that would be day over day interactions. The first row in V transpose is going to represent the most dominant frequency, the most dominant pattern that you have in your signal, right? And similarly, the first column in U is going to represent kind of the trend over the last n weeks. Okay, so now that we've done vanilla singular value decomposition, we're going to take the next step, which is we're going to decrement all of the singular values by a constant fixed parameter, right? And actually, in the first version of this code, it was fixed, but we've since gone back and made it adaptive, where it's a function of the energy of the noise. And so that's made it actually a parameter-free algorithm, which is pretty elegant. But you know, for now, just think about decrementing by some constant amount, where I'm never going to decrement the singular values past 0, right? By definition, you can't, singular values are all positive, so I can never have a negative singular value, so I would never decrement it past 0, right? So I've applied a maximum at 0 here. Okay, so after one piece of intuition about this is, if the way that most people think about singular values is they say people usually think that there's like a cutoff, right? They say, oh, I'm going to choose enough singular values to represent 95% of my signal, right? I'm going to get rid of 5% of the variance in my signal. Another thing they might say is I'm going to choose the top n most substantial singular values. But what's really happening here is I'm saying I don't really understand how my anomalies are distributed across my singular values or my singular vectors. And so I'm going to just kind of uniformly decrement them all. I'm going to penalize everybody with the hope that by introducing that little bit of noise, I actually instigate or excite some new mode in the system that gets kind of re-exaggerated in the next iteration. So this is an iterative process. And so I think that's something that's fundamentally different about RPCA versus the singular value decomposition, is that we don't really have to go through the process of tuning this, right? And this is one of the things that makes it more robust, is that there's no human knowledge required. If I had to go through for each one of our 100 signals for 100 fact tables, that'd be, even that many time series would be ridiculous to try and tune on my own. So the fact that this is parameter-free is pretty elegant. Okay, so then I'm going to do something really simple. I'm just going to calculate the residual from this. And then once I have the residual, I'm going to apply something that looks very, very similar to the previous kind of decrement, but I'm going to do it to the error, right? So rather than driving everything towards negative infinity, I'm going to drive everything towards 0. And so in this particular case, this is what the function looks like. And lambda here is another parameter that's determined automatically by the algorithm. And as the algorithm converges, O is going to contain the outliers. So then, before I start the next iteration, I subtract what my candidate outliers are from my original system, and then I start the next iteration. Okay, so this is just another matrix decomposition that you can use. And so it's been fun for us to think about all the different places where we're using the singular value decomposition and just replace it with RPCA for free. PCA is really just a singular value decomposition of a covariance matrix. And so, or a correlation matrix, depending on how you think about it, whatever. I'll let you have your opinion. But so to think about applying this kind of robust singular value decomposition on other problems is a pretty attractive thing. So some other places where we've done this in the context of anomaly detection is through correspondence analysis. So correspondence analysis is, rather than trying to decompose the variance of a system, you try to decompose the chi-squared distribution. So you can imagine a matrix where each element in that matrix represents some deviation from the pooled distribution. And then if you decompose that, then you get a sense of how your kind of uncertainty, right? The elements of your statistical tests that are really driving statistical significance are distributed. And so this has been easy kind of gimme. And then the second easy gimme has been, ARIMA is a really popular time series modeling mechanism, but really this has all the same problems that regression has, and regression has all the same problems that a singular value decomposition has. And so it's been fun for us to think about other more robust realization systems where you can represent a time series as an arbitrary AX, A times X plus B times U, where we're trying to solve for A as a function of some robust singular value decomposition. Okay. All right, so that's what we've been doing on the anomaly detection front. On the evaluation front, we're doing something really awesome, and I was disappointed that I couldn't share the actual output of it here for the first time, but we're so close. We're so close. And so what we're doing is, I'm going to skip this slide. We've introduced stochastic unit tests to all of our anomaly detection algorithms. And so this gives us the ability to do regression testing on any change that we introduce. And it also gives us the ability to compare algorithms one against each other. So you can think of the output of any algorithm for any data set generator as a confusion matrix, right? And then you can compare these confusion matrices with each other to get a sense of how well algorithms perform in different settings. And so this is one thing that we're doing, which is great, and I would encourage you to kind of keep a pulse on the Netflix tech blog over the next couple of weeks, because I think we're going to release something pretty soon on this. And then once we do, I would absolutely encourage you to partner up with us on it. There are lots of great groups doing anomaly detection work at other places, like Yahoo's doing a bunch of great stuff right now. There's some academic work in Europe and also domestically. And we'd love to partner up with you and just try to have a more academic and thoughtful way of analyzing these different algorithms in the context of their implementations. The other thing that we're doing is we're doing non-stochastic unit tests, where we've built a UI. Well, this isn't my team. This is Karen, who I think she might be here. I don't know if she's here. Karen's team is actually building a data tagger where Netflix data is being naturally tagged, and we're just accumulating all this stuff. And we're trying to decide how to use this. We're trying to decide how to use this data and to better improve algorithms, not only at Netflix, but generally speaking. And I think there could be some great opportunities for collaboration around the data tagger data as well. All right, so one last thing I wanted to say is that, I've talked a little bit about our tech stack and some of the things that we're doing on the anomaly detection front. But Netflix has we have a pretty strong culture, and we're not just about technology. And I'd really encourage you guys, if you're not familiar with it, to go check out the Netflix culture deck. This is like a set of values that we really strive to live by as a company. And I think this has changed the way, it's certainly since I've joined Netflix, it's changed the way that I think about business and management and decision-making and all these things. And so I'd encourage you to look at that and come talk to me with any questions that you have. So thanks, guys. Appreciate your time. I'll take some questions if you have some, or we can just meet out in the foyer and go have some beer. It's up to you guys. Actually, no, Dawn is up next. So I will be here for that, and then I'll be drinking beer with Dawn after that. So questions? Yeah?
You mentioned that you have several algorithms that vote and that must be seeing new one.
Yep.
Which other algorithms participate in this voting?
Yeah, so there's, okay, so ESG grubs, is an algorithm. It's basically like z-scoring on normal distributions, where at every check, you apply a statistical significance test to reject whether or not that's actually an anomaly. So this is something that Twitter really pioneered, and we've been using it pretty successfully at Netflix. We use dbScan heavily, and then we have autoencoder, And we have a fourth one that I can't remember right now. But it's not just that all of these are voting together, but there's different representations of all these too. So like we have multiple representations of the same, so because of the way that we hash data, we naturally get multiple representations of the same data element. And so we get natural voting through even the implementation of one algorithm. We can talk about it more offline, but yeah, those are the kind of 5 currently. So the 4 that I mentioned, plus the one I couldn't remember. Any other questions? Oh yeah, go for it.
You mentioned that you guys were working on some research for compressing matrices. Should I watch the Netflix tech talk, or where's that going to show up?
Research for compressing matrices.
You mentioned hashings.
Hashing. Yeah, that'll definitely be part of the tech blog post. Yep, definitely. Yep. Any other questions? Go for it.
Can you say what exactly you mean by stochastic unit tests?
Yeah. All right, so stochastic unit test. It's kind of, yeah, it's not a really good use of the word unit test. So the idea is all of these algorithms have an expected range of performance. And, you know, if you did a Monte Carlo simulation where you expose each one of these algorithms to, you know, just you hit it 100,000 times with the same distribution, then you would expect the output of the algorithm to be something close to, you know, consistent with past observations. And so that's basically what it is. It's a unit test that runs. It's a Monte Carlo simulation that checks to make sure that the posterior distribution is within an acceptable bound. Make sense?
It's just deterministic, but you run like 1,000 simulations each time.
It's deterministic in the sense that we run the same number of simulations, but it's random in the sense that the initial condition of the random number generator is always different. So, yeah.
That could sometimes fail and sometimes not.
It could technically fail. If we have our p-value set improperly, then it could definitely fail. I've been pretty conservative. So, any other questions? Yeah?
So if you were to explain how you go about anomaly detection to someone in kindergarten, would you say your first steps would be you compress the information, which then like the anomaly brings out through hashing? So like hashing becomes a way to bring about some of that anomaly detection. And then the next step would be to add noise to then like terrorize the anomalies to make them rise to the surface.
Let's take this question offline.
All right.
You and I can talk about it later. All right, guys. Hey, thanks so much. Appreciate your time.